Hello everyone, welcome to Back to Basics. And today we'll be covering special triangles, how we derive them, as well as using them to solve for missing variables. So special triangles are essentially just right-angled triangles with specific angles and side lengths that'll stay throughout your mathematical journey. And you do not need a calculator to be able to solve for any of these missing variables. Now, where do these special triangles come from? Well, the first case, let's take a look at this equilateral. As we know, an equilateral triangle is where all of the angles and the side lengths are the same value. In this case, all of the side lengths are equal to 2. All of the angles are equal to 60 degrees. Now, this is obviously not a right angle triangle, but we can build our own right angle triangle by simply dividing this equilateral perfectly in half. So I'll just show you right over here. We'll simply just draw a line down the middle to the right, to the base of the triangle, creating two right angle triangles. Now, of course, since we divided this triangle into two, our base's side length value would obviously change. Since 2 divided by 2 is simply 1, so then we'll put 1 for each of the specific right angle triangle. Now this angle up here has been perfectly divided by 2, so then 60 divided by 2 is simply 30 degrees. Now we have created a right angle triangle. So first, when we create our right angle triangle, we have to be able to distinguish our hypotenuse, adjacent, and opposite to be able to actually solve and use the primary trig ratios to be able to solve for the missing variables. However, in this case, we are missing this length. We don't know the value of the length of this triangle. So going over here, I will fill in the triangle. We know our hypotenuse is always opposite to the right angle itself, so that stays consistent. And now we're trying to solve for either the adjacent or the opposite. The reason why I say this is the adjacent or the opposite is because it really depends on the specific angle you are looking at this triangle from, or the perspective. Let's take 60 degrees over here at the bottom. That means 60 degrees, the side length directly opposite to 60 is this one over here. So then this will be the opposite rather than the adjacent. However, the same could be said for the 30 degrees over here. The 1 is essentially directly opposite to the angle itself. So then the side length 1 will essentially be your opposite. Now, to be able to solve for this missing side, we have to use Pythagoras' theorem, which is c squared is equal to a squared plus b squared. We know our c will always be the hypotenuse, or in this case, 2. And the a or the b will either be the opposite or the adjacent. So in this case, I'll just rearrange to solve for a. Now, to isolate for a, now to plug in our values, we'll have 2 squared minus 1 squared is equal to a. This will give you root 3. Now just keep it as root 3, as decimals are essentially rounded values. So they won't give you the exact value that your teachers would want. So in this case, this side length is equal to root 3. Now let's take a look at another case. Now for this one, this angle is 45 degrees. That means if it's a right angle triangle, 180 minus 90 minus 45 essentially just gives you 45 degrees for the other angle. Now, if you remember back to our geometry, this quite oddly looks like an isosceles triangle, which means 2 of the angles and 2 of the sides are congruent. Now we're trying to solve for this missing side length, or in other words, the hypotenuse. So if we just have 1 over here and side length 1 over here, this creates an isosceles triangle with a right angle. So now to be able to solve for the hypotenuse, which is the missing side length in this case, we'll just simply use Pythagoras' theorem again. So c squared is equal to a squared plus b squared. If we set c as our hypotenuse, that means we will just take the root and isolate for c. And this will essentially equal to 1 squared plus 1 squared, which c will equal to just root 2. So our hypotenuse for this isosceles triangle is simply root 2. Now we have our special triangles. Let's take a recap. So you can try to pause the video and then solve for these 2 special triangles. So I'll just quickly go over them. This missing angle is 30 degrees. Our A, in this case, the hypotenuse, is equal to 2. Our C is equal to root 3. And our B over here is equal to 1. It obviously takes a lot of time to be able to memorize, but once we start to do problems using these special triangles, they become a lot easier to recall. Now this one, our angle C will be 45 degrees. Our side length C will be 1. And the other side length A will also be 1. And our side length B will be root 2. Now let's use these special triangles to be able to solve for specific problems over here. So to be able to solve for our primary trig ratios, we have to actually use SOHCAHTOA. Or if anyone remembers, in this case, are these trig ratios. Now let's take a look at tan 45 is equal to what? We know that tan theta is equal to the opposite over the adjacent. Now, because it has 45 degrees, this triangle we won't be able to use because there's no angle that's equivalent to 45. But this special triangle over here, there are angles equivalent to 45. So if we just look at it from this perspective, our opposites to 45 degrees is 1. And adjacent to 45 degrees is also 1. So in this case, tan 45 is simply equal to 1. Let's take a look at sine 45. Sine theta is equal to the opposite over the hypotenuse. My equal sign looks like a Z. Sorry about that. Now, this triangle obviously doesn't have 45 degrees, so we have to look at this triangle again. So what is opposite to angle 45 is 1. And our hypotenuse is root 2. So sine 45 is equal to 1 over root 2. Let's take a look at sine 30. We know sine theta is equal to opposite over hypotenuse. So angle 30 degrees is over here. Now what is opposite, or the side length opposite to 30, is 1. And our hypotenuse is 2. So essentially, sine 30 is equal to 1 over 2. Now you can obviously put all of these angles into your calculator, such as if we put sine 30 into our calculator in degree mode, we will get 0.5, which is 1 over 2. Now let's take a look at these two questions where we have to solve for the angle itself. In this case, we'll just do the same. Write out your trig ratio, cos theta, which is the angle we're trying to solve for, is equal to the adjacent over the hypotenuse. Now all you need to do is take a look at these special triangles and look at if the number 1 and the number 2 exists. Let's take a look at the top one. Obviously the number 1 exists, however 2 does not. We have root 2 instead. So we know that theta does not equal 45 degrees. Now let's take a look at the bottom triangle over here. We see a 1 and we see a 2. So the 2 is the hypotenuse, and the 1 can either be the adjacent or the opposite. So now we have to look at our trig ratio itself. We know the numerator, or the adjacent, is adjacent to the angle itself. So the angle that is adjacent to 1 is 60 degrees over here. And hypotenuse, it will always be opposite to the right angle, so in that case is 2. So this cos theta is equal to essentially 1 over 2. Theta is equal to 60 degrees. Now let's take a look at tan theta is equal to 1, or tan question mark 1. We know the trig ratio for tan is tan theta is equal to the opposite over the adjacent. And in this case, we're looking for the number 1. Now we obviously have 1 in both of these special triangles. However, we have to know that our fraction, or the opposite or the adjacent, they have to divide out to equal to 1. So if you take a look at this triangle over here, 1 divided by 2, or 1 divided by root 3, or root 3 divided by 2, they all don't equal 1. However, this triangle up here, we have 1 and 1 as the side lengths, and when we divide out 1 divided by 1, it still equals to 1. So in this case, our theta is equal to 45 degrees. Thank you for listening, and hope you have a wonderful day.